So here we are at Winchester National Cemetery, and I bet you're wondering what we're doing here today and why you're watching a video taken in a cemetery for an earth science class. These are all good questions. The reality is, we're out here to do some field work. I do have a thing for cemeteries. There's a lot of really interesting things to see and to read about. What's also nice with cemeteries is they're a great source of data, especially when it comes to stone. And the great thing about military cemeteries in particular is the uniformity of material. Every single monument here, with the exception of the noteworthy exception of the obelisks and some of the other and the big monuments, but all the gravestones are made of marble. And marble is a metamorphic form of limestone. Limestone being the parent rock of that. But in both cases, they're made from calcium carbonate, produced originally on the bottom of the ocean when marine microorganisms like foraminiferae and so forth would die, and they would accumulate on the seafloor. And over a long period of time, that accumulation those accumulations would get compacted and then lithified into what we call limestone. And then mountain building events, which came much later, would turn that limestone through heat and pressure into the metamorphic rock marble. And that's what you see here. And the marble often has nice, well, marbling to it. You can see some of the stones have display that. You get the streaks and the swirls and so forth. Marble's been used for many millennia for monuments. And it's easy to carve, it's soft, the grain size is small, so you can get really nice intricate carvings with it. But what else is nice about marble is that because it's calcium carbonate, it reacts well with acid rain. So over time, chemical weathering does its thing. So the calcium carbonate reacts with the carbonic acid, that is the rainfall, or that's in the rainfall, right, the water. And that carbonic acid begins to breaks down the monuments over time. Now, the nice thing about this cemetery as well is there aren't a lot of trees. So all these monuments are getting the same treatment in terms of weathering. There's a lot of uniformity in terms of with regard to the weathering that's going on here. So, you know, you might have a large tree like in front of me here that could actually be significantly affecting over time the degree of weathering or the way that the stone is weathered. So if I'm going to use this use a cemetery like this and these stones as data, as a source of data for something, then I need to have as much uniformity as possible. Like any good scientific experiment, I want to eliminate as many of the extra variables as I can to try to isolate the one that I'm looking for, the one that I'm trying to measure. In this case, we're trying to measure weathering rates. You're going to read a couple of articles that discuss the use of cemeteries for weathering rates, to determining weathering rates. And the whole idea is, you know, that these cemeteries, that these monuments wear down over time. And of course, that's important to note. So let's look at this one here. We have James Edward Jackson Sr., West Virginia, World War I. This monument was erected in 1969. So this is a nice piece of marble, and if we are thinking about how the rainfall would hit this monument, our assumptions might be that the rainfall hits it on the top of the monument most vociferously or most intensely, and at the bottom of the monument it gets hit by rainfall, but not as much. And actually the bottom of the monument probably gets hit more by weed whackers than anything else. But here's the thing, it's not just that. The rainfall that does hit the top does make its way down around the monument and make its way down along the sides, the front, and the back. However, by the time it's gotten down some distance from the top, any acidity in the rainfall is likely to have been buffered at that point. In other words, it's not acidic any longer. It's neutral. And so, the hypothesis goes that if the acid rain hits the marble, it's going to do most of its work, most of its weathering on the top of the monument and less at the bottom of the monument. So that, assuming that everything is uniform when this monument was created, in other words, the slab was cut exactly by pretty exacting standards initially, and that the marble itself doesn't have a lot of impurities in it, that the stone was indeed erected in the year indicated, we can use that year minus the current year as one of our variables. And then we have the other one is looking at the width of the top and the width of the base. If the top of this is weathering at a higher rate, then we would expect the top to be narrower on average than the bottom. And so then we can subtract the top's average from the bottom average. So we're going to take a couple measurements here. We're going to do a measurement here, a measurement here, we'll do a measurement here, we'll do a measurement here, and then one on the top. So 5 measurements in all, okay? In order to do that, I'm going to use a set of calipers. These are convenient. They're going to measure in millimeters. And of course, like any good field researcher, I'm going to take notes. I'm going to write my data down. So in order to do this, what we would do is start by indicating some of the data that's on the tombstone here. So we would describe the material, okay, which is marble. I'll make an M for marble. I'd note the year, 1969. And then I'm going to go ahead and get ready to take my measurements. I'm going to go with the left base, which this is the face of the monument. I'm going to say this is left, this is right. So I'm going to go with left base, left top, right top, and center top. To do this, I make sure that I zero my calipers. And then I'm simply going to open them up. And of course, these calipers have two sides. They've got the side where you can measure the inside of something, and then of course the other end where you can measure the outside of something. And I'm going to